Hey everyone, today I'll be going over questions 1 through 3 of weekly contest 248. Question 4, I took a look and it's quite complicated. It uses a rolling hash, which I am not that familiar with, and so I don't think I'd be suited to try to explain the solution. So this contest happened live yesterday, and I wasn't able to do it live, but I just worked through the first 3 problems today morning, and did them actually pretty quickly because I thought they were pretty straightforward. So I'm going to be making a video on the first 3 questions. So let's get right into it. So in the first question, you want to build an array from an input array. From an input array, and the number that goes inside of the ith index is equal to like this little equation here. So if we look at this number array and we take a look, let's say, at the first index, so this index 1, then that's 2. So then we will look at index 2, and that's the number we need to put in our answer array at index 1. And the same logic keeps on going. So for example, for index 2, we look at this number and it's index 1, and we put this in. So this problem, we just do exactly as it says. So for index I in our answer array, that should be equal to this expression. So what we do is we just go through each I that we need to in our answer array, and we set that equal to this expression and return it. So yeah, and this gets accepted. And yeah, so the first question is fairly easy, which explains the high acceptance rate. So now let's look at the second question. Basically, to simplify it, instead of this big setup, essentially each index you're given 2 arrays of the same length, and each index in it corresponds to a monster. So index 0 means that there's a monster 1 meter away and it moves at 1 meter a second. Index 1 means that there's a monster 3 meters away and it moves at 1 meters per second, and so on. And as you can see, there's multiple different things. You have to say the number, and every second you can kill a monster. And basically you have to output the number of monsters you can kill. So, and if a monster reaches your city, then you lose. Basically that means their distance equals 0. So, for example, in this first test case here, in the first second, you should kill this monster, because after 1 second, this monster will reach your city because it's 1 meter away and moves at 1 meter a second. So at, sorry, not seconds. I think they record it in minutes, but it doesn't really matter. So I'll just use minutes from now on. So, yeah, so at the start of minute 0, you have to kill this first monster. And so the solution to this problem is that we can use a greedy solution. We want to always kill the monster that will reach our city the fastest. So we can tell how long it'll take for them to reach our city by dividing the distance by the speed. So for example, 1 divided by 1, that means at minute 1, this monster will reach our city. So we have to kill it before minute 1. So that's at minute 0. And every minute we can kill 1 monster. So in this monster, 3 divided by 1, that means at minute 3, this monster will reach our city. So we have to kill it at either minute 0, 1, or 2, and so on. So we'll sort these monsters by the time it takes for them to get to our city, and then kill them off starting from the fastest to the slowest. So let's look at how that's implemented. So first of all, we'll just make a class, and it'll have, we really only need the time, but I just had this because I didn't plan it out completely. So to calculate the time it'll take for the monster to reach our city, we will divide the distance by the speed. And then we will perform this check. If the distance is not perfectly divisible by the speed, we need to add 1. To see why this is the case, we'll look at a simple example where, let's just say, sorry, let me just get rid of this. Let's just say we have a distance of 4 and a speed of 3. So 4 divided by 3 with integer division, that equals 1. And however, after 1 second, this monster that moves at 3 meters a second, after 1 minute, this monster that moves at 3 meters per minute will still be 1 meter away. So it will take 2 minutes before the monster can reach our city. So basically that means we can kill it either at minute 0 or minute 1. We just have to kill it before minute 2, because at minute 1 it'll be 1 meter away, and at minute 0 it'll be 4 meters away. Neither of them are 0 meters away, so they haven't reached our city yet. So we'll just have a priority queue that sorts these monsters based on their time. So the faster monsters are first in the priority queue. So yeah, and we will just create a new monster for every monster that we have by looping through the array. And then we will have a time. This represents the number of minutes that are passed. So at first it is minute 0, as you can see from the test cases. So while there are monsters left to kill, and the next monster, like, we're in time to kill it, so then we kill that monster by removing it, and we add 1 to our time. So something, this would play out something like this. So originally we start at minute 0. Then we peek at the first monster. We see that it will arrive at minute 1, and we know minute 0 is before minute 1, the time of arrival, and so we will remove that monster and add 1 to time, because we eliminated a monster at time equals 0. And now our minute will equal 1, and we will see if the next closest monster is takes more than 1 minute to reach our city. And if so, we'll keep on going. And we can return time, because conveniently time also represents the number of monsters we have killed. Every time we kill a monster, which is removing it from the queue, we will add 1 to time. So this will represent the number of monsters we killed, and that's exactly what they want. So if we submit this, it gets accepted, and the runtime of this would be n log n, and because n is 10 to the 5, that's a viable solution. Now let's move on to the third question, count good numbers. So in this question, you're given I think it's an integer or a long. Yeah, you're given a long n. And n can be from 1 to 10 to the 15. And what this means is this is the length of the like digit string. So this would be a digit string of length 4. And a digit string is good if all the integers at even indexes are even and all the digits at odd indices are prime. So in this example, so prime numbers are 2, 3, 5, or 7. Those are the prime digits. So these are just some examples of what would be counted as a good digit string or a not good digit string. And you're supposed to return the total number of digit strings of length n, and return that modulo 10 to the 9 plus 7. So the first observation we need to make here is that because n can be so large, we are looking for a constant time solution that we can evaluate mathematically instead of using some sort of brute force checking all the good numbers approach. And another key observation that will help us is that a digit string can have leading zeros. So to understand the solution, we need to first figure out how to calculate this mathematically. So if we have a digit, if we have a restriction of n equals 4, let's just say hypothetically, we know we will be looking for digit strings of length 4. We know at even indexes there will be options to put a 0, because leading zeros are allowed, 2, 4, 6, and 8. Those are all the digits that can appear at even indexes, so index 0, index 2, etc. So there are 5 options every time. So our even length sequence, we know there will be 5 options here and 5 options here. So there will be 25 total options because we do 5 to the power of 2 because there are 2 even indexes. So there are 25 total options for the generation of these two numbers. So that can be like 0, 2, or 0, 0, etc. And since there are 5 options here and 5 options here, we can just multiply them. We can use the same logic for our odd indexes. So as they give here, the prime digits are 2, 3, 5, and 7. And so we know there will be 2 odd indices, and each of them will have 4 options. Similarly, we can mathematically calculate how many sequences of these odd digits there are just by raising 4 to the power of 2. There are two spaces. Each space has 4 different options, so we can just multiply the 2. So it's 4 times 4, and that would equal 16. Next, what we can do is we know there are 25 options for the even like choices, so like 0, 0, 2, whatever. So for each option, let's just say one option is putting zeros in all of them. For each option, we know we can pair it with one of the prime things. So we can pair 0, 0, 0 with all the 2's, and then we can also pair it with like 2, 3, ... and fill it all out. So we know for each of these 25 even sequences, we can pair it with each of the 16 odd sequences. So to get our answer, we can do 25, multiply that by 16, and that's our answer. But we need to modulus it by 10 to the 9 plus 7 to cast it into an integer. So this is the basis of our solution, but there's one big problem. Because n can be so large, 10 to the 15, we might be needing to raise 5 to the power of like a very, 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 very large number, far too large to hold in a simple, like long even. So we need to be a bit clever about how we perform this exponentiation operation. So now we move on to the next part of the solution. So to recap, given an integer n, what we want to do is we know we're looking for answers of length n, right? So there will be even indexes at these indexes. And if n is odd, let's just say there's an odd number of spaces, so we add another one, there will be one more even index. So to find the number of even indexes, we can do n plus 1 divided by 2. That's even. That's the number of even indexes. And the number of odd indexes is just n divided by 2. And now we know that our answer will equal 5 to the power of even multiplied by 4 to the power of odd. And we need to modulus this by 10 to the 9 plus 7. Now, our challenge right now is to find a good way to perform this operation. So we need to make use of the fact that A times B mod C, that is the same as A mod C times B mod C, mod C. So you can sort of distribute this C inside and but still keep it outside like this. So what that means is to calculate this power, we can do a little trick. So we can first divide this exponent by 2. So we'll calculate 5 to the even divide by 2. So let's just assign that to a number. Let's call it P. Then to know what 5 to the power of even is, we'll do P times P. And the clever thing we can do about this is, if we do this recursively by continuously dividing by 2, we can do P times P and then modulus the mod operator. So let's just say C equals 10 to the 9 plus 7. So we can modulus that, and then what we can do is this will bring up into this iteration, and we will multiply them together and modulus that again. So we'll essentially be performing this modulus operator every single time we go double the power. And we just need one more check here. If this number is not divisible by 2, we just need to multiply this one more time by 5, because we're raising 5 to the power of even. And this will allow us to calculate 5 to the power of even modulus C. And we can repeat the same thing to calculate 4 to the power of odd modulus C, and then modulus that by C again. So we're taking the modulus of this number, so we never get the true 5 to the power of a huge number. We are just getting the modulus version of that, and the modulus version of this, and then we're modulusing that again. So we're making use of this little formula here. So if we take a look at how that's implemented, we will have our power function that raises one number to the power of another. If the second number is 0, we will return 1, because that's how powers work. Otherwise, we will find this divide by 2, and this will recursively go on. And then we square it. So now we will have x to the power of y. But if y is not perfectly divisible by 2, we need to multiply that by x one more time to have the true power. And then next we will modulus that. So if you imagine this recursive function, we will constantly find this number and then modulus it, and then keep on modulusing it. So this will give us 5 to the power of even modulus this number, because we're constantly making use of this modulus operator. Because what essentially we're doing is, if we pretend A and B both equal P, this is what essentially we're doing. And then what we can do is we can just multiply them together and modulus them again. And this will give us 5 to the power of even, so this is even, and 4 to the power of odd, and we modulus them both. And so by doing this modulus operator every single time we perform this power operator, we will essentially be able to calculate what 5 to the even modulus c, which is this number, is without ever needing to store this huge number here. And so if we submit this, it gets accepted. And yeah, so this is quite a clever way to get the power operator but still keep it modulus. And yeah, so that's about it for this video. Hope you enjoyed, and I'll see you guys later.